Okay, let's look at solving two-dimensional systems of linear equations in this video. And we're going to focus on two things. We're going to focus on using a technique called substitution, and we're going to focus on the case where the system has one solution. Okay, so let's talk about a system of two-dimensional linear equations first of all. Basically, geometrically, what we're talking about, when we're talking two-dimensional linear equations, we're talking about equations of lines in two dimensions. So if we're talking about a system, then we're going to be working with two linear equations. Not just one, it'll become a system of two equations now. And so geometrically, what that means is you're going to have one line in two dimensions, and you're going to have another line in two dimensions. And when you're going to solve a system that involves two lines, what you're trying to do is find any ordered pair, right? You're in two dimensions, so you need an ordered pair, an x and a y, that make both equations true. And what that means geometrically is you're trying to find the point of intersection, okay? So in most cases, it's most common that when you create two lines, you're going to intersect at one point. And so that's what this video is going to focus on, is how do you find that point of intersection? And we're going to do it using this technique called substitution, which is an algebraic technique. There's not going to be any graphing here to actually solve. But that's geometrically, that's what that's discussing. Now you can have other cases, of course, where the two lines happen to run parallel, which will never intersect. That's a case that has no solution. We're not going to look at that here. There's a case where both lines could be the same line. They could lie right on top of each other and they intersect at an infinite number of points. We're not going to look at that case either. Those are kind of the more rare cases. So we'll start with this first system. And the way we write a system is we write our two equations. So let's say our first equation is 2x minus 3y. 2x minus 3y equals 9. And our next equation is x equals 4y minus 1. So those are our two equations. Now we need to put them into a system, which is commonly done by putting a left brace adjacent to both equations. Okay? So that's typically the notation for a system. And the instructions that might accompany a system like this would be maybe solve. Solve. And the word solve here again means find any ordered pairs. In this case, we're going to find one. That's the most common case. Find any ordered pairs, or find all ordered pairs that make this equation true. In other words, geometrically, all ordered pairs on this line. And find ordered pairs that are on this line that are also on this line. In other words, make this equation true also. Okay, so let's get down to business on how the substitution technique works here. This system is set up beautifully for substitution. The reason for that is this second equation, let's label these. This is equation 2 and this is equation 1. Okay? Equation 2 already has one of the variables by itself. We already have an expression for x. And so what we can do is we can take equation 1, 2x minus 3y equals 9, and I can substitute what x is, which is 4y minus 1, I can substitute that in for the x in equation 1. So that looks like 2 times x, well that's the same thing as 2 times 4y minus 1 minus 3y equals 9. So all I did was replace my x in equation 1 with its representation from equation 2. You need this sort of mix of the two equations to start to identify what the variables x and y are, what the ordered pair is. And so the beauty of substitution is this. We had this equation in two variables, meaning two unknowns that we couldn't figure out either one. Okay? But now, when I replaced x with y stuff, my new equation is all just based on y. It's one variable. And we can figure out what that one variable is using basic algebra. So now if we solve this, we're going to get the y part of our ordered pair. So I'll distribute my 2 to get 8y minus 2 minus 3y equals 9. And then it's basic algebra. 8y minus 3y is 5y. Let's add the 2 over to get 11. And so if we divide by 5, we see that y is 11/5. And we've got the 1/2 of our ordered pair for our final solution. Okay? But now that I have my y, I need to know my x. And at this point, I can take my y and substitute again. Now since I have y, I can substitute y back into either one of these two equations, whichever one. You should try both if you want to see it. But the best choice here is going to be to plug it back into equation 2. Because equation 2 already has x by itself, I can plug it in, and it's going to turn into x equals 4 times y, which is 11/5, minus 1, okay? So I just substituted our y value back into equation 2, and now all I have to do is calculate this number to get x. So this is 44/5 minus 1, which is 5/5. So x is 39/5. So the final solution to the system, is the ordered pair where x is 39/5 and y is 11/5, okay? So that's the answer. This ordered pair makes the first equation true and it makes the second equation true. This ordered pair is where these two lines would cross one another. Now, just for practice, just so you can see this, we're gonna check that this ordered pair actually makes both equations true. So let's check that. You don't always have to do this, but it's certainly good at least this first time. So I'm going to plug 39/5 in for x and 11/5 in for y. So 2 times 39/5 minus 3 times 11/5 equals 9. And we want to know, is that true? Well, 2 times 39/5 is 78/5. Minus 3 times 11/5 is 33/5. 78 minus 33 is 45. So we get 45/5 equals 9. And that's true. 45 divided by 5 does equal 9. So this ordered pair is a solution to the first equation. If we check the second equation, we get x equals 4y minus 1. So 39/5 is x equals 4 times y, 11/5, minus 1. Is that true? So we get 39/5 on the left, 44/5 minus 1, well that's 5/5. And 39/5 does equal 44/5 minus 5/5. So that's true also. So we can in fact verify that this ordered pair is the solution to both equations. And again, geometrically, if we were to graph those lines, this would be the point where the two lines would cross. Okay, so this was a good example to start with because it was set up beautifully for substitution. We already had x isolated in one of the equations, so it was very easy to say, okay, let's plug 4y minus 1 in for x. So let's look at a couple other cases. Because there are other techniques to solve systems, so it's nice to be able to think about in certain cases which technique is going to be better. This one is perfect for substitution. All right, now let's move a little faster as we go along. Let's try another example. Let's say we want to solve this system. X plus 4y equals 8, and 2x minus 3y equals negative 6. Okay? All right, so what we'll do is neither one of these has x or y by itself, so we can't go directly to substitution. But what we can do, let's label this equation 1 and this equation 2. That's always nice to do so you can refer back to them through the process and kind of make your work easy to follow. Mostly for yourself, because if you make a mistake, it can be very difficult to track your work unless you stay organized. And that's one of the key aspects of solving systems. All right, so if we're looking at equation 1 and equation 2, and we want to get x or y by itself, there's a best choice in this case. Now, you could take equation 2, for example, and you could get x by itself. But if you did, you'd have to divide by 2 eventually, and you'd get fractions, okay? And that's okay. You can work with the fractions. You should practice that. You should be comfortable with fractions. You could get y by itself, but you'd have to divide by 3, and you would get fractions. In the same case, equation 1, you're going to have to divide by 4. If you want to get y by itself, you'll have fractions. The only way to avoid the fractions, which we might want to choose to do, is to get x by itself in equation 1. So to get x by itself, I'm going to subtract 4y. So that'll be x equals 8 minus 4y. So this is my new equation 1, and this is my equation 2. So what I can do now is I can take and I can substitute this x into equation 2 for this x. So I'll label equation 2. I'll write 2 times x, which is 8 minus 4y, minus 3y equals negative 6. And you can see after performing the substitution, there's only one variable that remains here. It's y. So it's just like the last example now. By the way, there's nothing special about getting x by itself. If this was y, then I would get y by itself. It doesn't matter. Again, we could have gotten any of these isolated, but the x was the easiest. All right, distributing, we get 16 minus 8y minus 3y equals 6, negative 6. Negative 8y minus 3y is negative 11y. Subtract 16, giving us negative 22. Divide by negative 11, giving us positive 2. So now we have our y. And we need to get our x. So what we'll do is we'll go back to equation 1. In this case, that's easy to do. Equation 1 says that x equals 8 minus 4 times y, which is 2 in this case, right? Yes. Okay. So we get x equals 8 minus 8, which is 0. So the solution to this system is this very nice ordered pair, 0, 2. So this is the point where those two lines cross one another. Okay, and let's do one last example. Let's say we want to solve this system. Y equals 1/3 x minus 2, and also y equals 2x plus 5. Okay, so in this case, this one's a bit different. The equations aren't in what we call standard form. They're actually in something we call slope-intercept form. That's fine. They can be in any form as long as they are two-dimensional equations, two-dimensional linear equations, which these are. If I want to use substitution, the way to do it is I need to know what x or y is. And luckily, I know what y is in two different forms. So in equation 1, y is 1/3 x minus 2, and in equation 2, y is 2x plus 5. So I've got two choices here. I know what y is in two different forms. So what we can do is, let's do this. Let's rewrite equation 1, right? Let's rewrite equation 1, but I'm going to replace this y, right, with this. Because equation 2 tells us that y is 2x plus 5, so that means I can call the y up here in equation 1 2x plus 5. So doing that, I get 2x plus 5 equals 1/3 x minus 2. And so now you can see when we do the substitution, the only variable that remains is x, and so we can get x by itself. So I'll subtract my 1/3 x over to be with my 2x. 2x is 6/3 x, minus 1/3 x is 5/3 x. Subtracting 5 over gives me -7. And then I can divide both sides by 5/3, which is the same thing as multiplying both sides by 3/5. Okay? Maybe show that one. Dividing by 5/3 is the same thing as multiplying by 3/5, and so those cancel and turn into 1, and this turns into -21/5. So now we know the x for the ordered pair where these two lines cross. Now let's go on to find our y. Let's go on to find our y. So if I want to find y, since both of these equations have y by themselves, I can plug this x into either one and I will get the same answer. Try it out for yourself. However, I see that equation 1 has a fraction in it. So I'm going to avoid equation 1 and I'm going to plug back into equation 2, which tells me that y equals 2x, but x is -21/5 plus 5. Okay? So y equals -42/5 plus 5 is the same thing as 25/5. So y is -17/5. So the solution, the point where those two lines cross, is the ordered pair -21/5, -17/5. And there are several different examples with solving two-dimensional systems by substitution that have one solution.